Good morning, class. Today we're going to take a look at an entire drainage network design example. Let me give you the overview of what we have. Before you get started, make sure you get a copy of a nomograph, a time of concentration nomograph, one for the pipe flow, one for the overland flow. Get those printed out or in a place where you can draw lines on those. So those are going to be needed for that. And you also have a separate PDF that shows this series of boxes here. Let's talk about what that is before we actually jump into the numbers on it. These are labeled, I'll just make it a little bit larger here, A, B, C, D, E, and F. And what we're looking at is a pipe network. This would be a series of catch basins and manholes that flow into a recharge basin. And at the end of today's video, we're going to do a little bit of talking about the end section of recharge basins and what we're expected to design those to look like. But what we have to remember on this is water flows downhill. It flows under the effects of gravity. There's no mechanical pumps adding energy into this, which would increase the speed artificially. So what we're going to do is we're going to look at the water flowing from A going into B. Then we're going to look at the water going from C going into B. Then B to D, D to E, and E to F. Now, along the way, I gave you some constraints. And the only reason I gave you constraints is that I want us to have some ideas of why we choose certain pipes for certain reasons. There will be cases where we want to keep the slope at a certain pitch because we want to make sure the pipe doesn't stick out of the ground. Okay, it's got to stay underneath whatever the road surface may be. There'll be times where we want to keep the velocity of the water either higher or lower depending on what's coming in. Again, we always want to keep that water speed between 2 and 8 feet per second. Those are our realistic numbers to keep it between. 5 is a great number to keep it at. The reason I like 5 is it gives you a little bit of wiggle room for the water to slow down, and it gives a little bit of wiggle room if we get excessive amounts of water in there and it starts to speed up a little bit. It doesn't, it's right in the middle. It's a good number to work with. And we're also going to have diameters that are going to be constraints for us as well. So we have slopes, diameters, velocity. We're going to take a look at all of those. So as we're going through this, I'm going to give you several times, I'm going to say, pause the video here and you do the calculation. This way, as we're going through it together, I'm going to continue on with the calculations, but I'd like you to stop the video. And as you stop it, then do the calcs on your own. And this way we can make sure that you're getting those numbers correct. All right, so let's jump right into pipe A to B. And we're going to solve these on the nomograph first, and then we'll solve it by hand as well. So going into A, we say that we have a Q equal to 5 cubic feet per second. We want to keep the velocity around 5 feet per second. Let's pick the slope of the pipe. Now, the only constraint we have on the pipe size is a 15-inch diameter. Why not anything smaller? Exactly, the dead cat rule. We don't want to go to 12 inches because if some animal dies inside of here and swells up, it's going to clog our pipe. So, moving over to the nomograph. 5 and 5, Q of 5, and a velocity of 5. And again, it's a lot easier doing this on paper than on a computer screen, but we'll try. 5 and 5. Okay, perfect. So that's 5 velocity and 5 for my Q. Remember on the nomographs, Q is here, velocity's here, that's my slope, that's my diameter. First pipe out of the design, we look at this and it's between 12 and 15. So where should we put it? If we bring it down to a 12, the pipe's going to be too small. So it's best for us to move it up to 15. In doing so, how do we want to deal with that? Let's try a couple different things. Let's look at first, if we change the Q to, keep the velocity, try it again, keep the diameter at 15, and we move the velocity down, we can still maintain the same Q coming in. There we go. So 5 cubic feet per second going into the pipe. It would flow through a 15-inch diameter pipe. That would give us a 4 foot per second speed. The other option, and this is the option we're going to actually use on this design. I'll do this one in green. Now I want to draw a line. What I want to do is I want to keep a 15-inch diameter, and I want to hold my velocity at 5. So 5 and 15. Now, why am I doing that? Let's go back to the initial requirements. On this one, keep the velocity at 5. The reason I want to do that is I want to force, in this particular design example, I want to force the velocity to stay 5 feet per second and show you how we have to carry that information forward. So watch what's going to happen. Based on the nomograph, we're going to go rough numbers and then we'll prove them out mathematically. Q would be equal to, and we're looking at the green line, 5 feet per second, 15-inch pipe, and we're going to be right around, looks like 6.4 CFS. Now on the slope, I should have mentioned we're going to use a 0.013 for all of these. So my slope will be 0.00, looks like 008, 7, 8, 9, maybe, yeah. Slope is around 0.0080. Again, plus or minus, it might be off just a little bit. So let's see what happens with those numbers. And that would also give us a velocity equal to 5 feet per second and a diameter equal to 15 inches. So that's what we're coming up with as our design based on the nomograph. Let's prove this out and see if that actually works. So what do we now know that is, we'll call it an absolute truth for this pipe. So for pipe AB, we know that the diameter is going to be 15 inches. That's a given. We know we want to keep the velocity at 5 feet per second. So what we're going to do then is we're going to solve for slope and we're going to solve for Q. So V is equal to 1.486 r to the 2/3 s to the 1/2 over n. When I bring everything to one side, slope is equal to Vn over 1.486 r to the 2/3 s to the 1/2, and all of that is squared. Excuse me. So this is a good point for you to pause it, do the calculation for slope, and if you can also Q, and when you come back, we'll go through the calculation. Welcome back. Slope. So this will be 5 times 0.013 over 1.486 times 15 over 12, 1.25 over 4 to the 2/3. I'm sorry, what do I have s to the 1/2 over here? And all that will be squared. So that gives me times 5 times 0.013 squared 0.0090. Okay, pretty close to what we had is 0.008, so that's good. That's my slope. How about Q? Q is equal to area times velocity. So this will be 1.25 squared pi over 4 times 5 feet per second. So Q will be 1.25 squared times pi divided by 4 times 5, 6.16, I'm sorry, 6.14 CFS, cubic feet per second. Okay, So those are our two numbers, 0.009 and a slope of 6.14. What do we do with that? Well, now that becomes important because this slope, 0.0090, and we're going to do inverts later on. We're going to use that slope to figure out what's happening with that pipe. But more importantly, how much water is flowing this way? There's two answers to this. I hate when there's two answers to a problem, but let's look at it one way. If you said you have 5 cubic feet per second, CFS, you're right. And if you said 6.14, you're also right. I think you're more right though. Okay, here's why. Even though we do have today 5 cubic feet per second flowing into that catch basin, because of the size of the pipe that we chose, and because of the speed that we're looking to keep the pipe pitched, keep the speed at 5 feet per second, and we chose a slope to make that occur, this pipe has the potential to handle 6.14 cubic feet per second. It's recommended, strongly recommended, and in this class I'd like you to do it this way. If a pipe has a potential for handling more water by calculation, carry that through. And the reason why you want to do that is that the installation of the pipe is the most expensive part of it. The size of the pipe, the diameter of the pipe, it doesn't really change the cost all that much. It's really the labor of excavating and backfilling and compacting. That's really where all the cost is. So if you increase the size of a pipe from, say, a 15-inch diameter to an 18-inch diameter, you're not talking about a tremendous amount of cost. If you went from a 15-inch to a 36-inch, yes, there would be a large change. But just to go a couple inches larger does not grossly affect the price of the project. So if you now carry that 6.14 cubic feet per second all the way through going into Basin B, then if at a later date this increases, your Q changes because of climate change or because the runoff coefficient changes from 0.3 to 0.5 or 0.5 to 0.7, whatever happens, it makes more water go into that basin. You've already designed a pipe that can handle it. So you now have a system that is future-proofed. You can put more water into that pipe at a later date. You don't need it today, but it's designed that later on you can if needed. All right, so 6.14 going into that basin. We'll remember that, and we'll start looking at pipe C to B.